in the primeval atom or the singularity. In the case of the primeval atom, the picture is that it exploded. In the case of the singularity, it just started to rapidly expand. Well, let's go to the primeval atom. When this thing exploded, all of a sudden, picture rushing out into space in all directions, these quarks. Now, there are 6 kinds of quarks. This physics has interesting names to these things. Up and down, charm and strange, top and bottom. Don't ask. But anyway, the 2 are going to be important to us are the ups and downs. Because these are the 2 that are going to go together to form the 2 fundamental components of atoms, namely protons and neutrons. Now, here's the way it works. The ups are worth plus 2/3 charge. Each up is a plus 2/3 charge. Downs are a minus 1/3 charge. So the way it works is, if you have 2 ups and 1 down, that's 2 times 2, 4/3, plus 1/3 down. If you subtract the 2, you end up with 3/3, which is 1. That forms the proton. That's why protons have charge of 1. On the other hand, if you have 2 downs, minus 2/3, 1 up, plus 2/3, they cancel each other out, and you have no charge. That's called a neutron. So your protons and neutrons are formed from the ups and the downs. And then, of course, what happens to the electrons, they simply are bundles of energy, and we know how that works. Now, the way it works then, now we have protons and neutrons, and these things go together to form the most fundamental atom of all, namely the hydrogen atom, which is 1 proton surrounded by 1 electron. Now, there were neutrons made into helium-2, but apparently there was not very much. The neutrons were used up very, very fast. So in our discussion, we're going to be talking primarily about the generation now of hydrogen atoms going out into space. Protons were being created. Out of the energy alone, electrons were being created, because that's all electrons are, just little bundles of energy. That would have happened with the primeval atom. How about the singularity? There wasn't anything there in the first place. Well, you got to make some matter. And how do you do that? Well, according to Albert Einstein, you can take his equation, E equals mc squared, and take energy and turn it into matter. And I presume the matter it was turned into would be the quarks. So in either case, we're forming the quarks, rushing out into space, and then the quarks started getting together to form the basic fundamental parts, protons and electrons. And then they say within probably a half an hour, which always cracks me up in a way, thinking about something that 13.7 billion years ago were broken down into half-hour segments. But they say within a half an hour, these things started getting together to make the most primitive of all atoms, a single proton, surrounded by a single electron, of course, hydrogen. So now if you could just imagine this bubble, if you will, of hydrogen roaring out into space in all directions. What was the next thing that happened? Well, the astronomers say little bundles of hydrogen started getting together. And I never could quite find out what caused them to do that, but they talk about these little bundles of hydrogen that started rotating on themselves. Now, I do know this. Isaac Newton taught us that in space, if you start to turn, which they were turning, you see, a force of gravity was generated perpendicular to the direction they were going, pointing toward the center of rotation. So picture now these little bundles of hydrogen starting to rotate, collapsing on themselves down into some core, and as they collapse down, some of that gravitational energy is being converted into heat. And they say that whenever the heat got up to about 15 million degrees in whatever measurement you want, what happened down in the core is 4 hydrogen atoms got together with 4 electrons to form 1 helium atom. Now, if you look at the mass of the 4 hydrogen atoms and the mass of 1 helium, 4 hydrogens has more mass than 1 helium. So it looks like we had some mass lost here someplace. Well, again, they tell us you can't lose mass, but you can convert it, according to Einstein's equation again. So that little bit of lost mass was converted into energy. So in addition to the helium, you're giving off all this energy, and of course what we've got now are stars. That's how stars were created. And stars were created through this expanding cloud of hydrogen gas. How much long it went on, we don't know. Maybe a million years, who knows? But sooner or later, the number of stars became so numerous that they started to attract each other. Because again, Isaac Newton taught us that everything in the universe attracts everything in the universe. So they started attracting each other into huge groups of stars called galaxies. Now, how big's a galaxy? How many stars? I really hadn't the slightest idea. Probably billions and billions, as Carl Sagan would have said. maybe 100 billion, maybe 150 billion into this huge group, and then it started to rotate. Now, things rotates like that starts to flatten out along the rotational axis. I think you probably remember from somewhere in your education that the Earth was, what, 27 miles shorter in the rotational axis than it is in the equatorial axis? Well, in this case, this mass of stars started collapsing down to form a discus shape. Now, there are all kinds of galaxies, I know, but the astronomers tell us that the general shape of a galaxy is a discus shape. Most of the stars being located at the center, as you might suspect, and as you get out to the outside edge, the number of stars get fewer and fewer and fewer. Well, of course, we belong. When I say we, our little private star, the Sun, belongs to one of these galaxies. We belong, of course, to the Milky Way galaxy, and we're located not all the way out to the outer edge, but pretty far out to the outer edge. It's sort of a neat place to be, because it's sort of like standing at the edge of the woods. You can look beyond the edge of the woods, across the field to the next woods on the other side. Well, in this case, we can look beyond the edge of our own galaxy, across space to the next galaxy, which is Andromeda. Had we been in the middle of the galaxy, I suppose we probably couldn't have done that, because the stars would have gotten in the way, like the trees would have gotten in the way if you were standing in the middle of the woods. So anyway, now we have this galaxy rotating us on its own axis. Galaxies started to form. How many galaxies are there? Well, again, I really don't know how many galaxies there are. Billions and billions, maybe 100 billion of these things, all rotating on their own axis, all rotating around space, around some point in space, I presume, where the Big Bang occurred, and all moving away from each other. Why? Because the universe is still expanding. We're still in an expanding universe. Question, how long will that go on? Well, again, I think that depends upon to whom you speak. For example, it depends upon how much matter is in the universe. Now, here's the real problem. We don't really know how much matter stuff is in the universe. We can see some of it. We can see stars. We can see planets. We can see those. But then there's the stuff that they call dark matter. We can't see dark matter. What dark matter is just bits and pieces of stuff we're going to talk about, cosmic dust. They're not big enough to give off much light. They don't give off their own light, so we really can't see them. So we call that dark matter. So the idea is that there's, they say, a critical mass of stuff. What that is, I've never had anybody explain to me exactly what critical mass is, but it has to be something beyond which something happens. Well, in this case, they say, if the known amount of mass we can see and the dark matter is less than this critical mass, then they say what will happen is the universe will expand forever. And then what's going to happen? Well, picture the universe expanding forever. It's expanding in space. There's no limits to space. So sooner or later, galaxies are going to get so far away from each other, you're not going to be able to see one from the other. And as they get further away from each other, as we're going to see for long, I'm talking about stars, the stars are going to start dying. And pretty soon, the universe is going to turn into a very cold, dark, dismal place. Not a place I think I'd like to be in. But that's if it's an expanding universe. That's called an open universe. On the other hand, if the total amount of known matter and dark matter is greater than this critical mass, what's going to happen is the universe is going to expand until a point is reached when gravity takes over and it says, okay, that's far enough, let's all go back. Now all we have to do is to crunch back, and just picture this now, as the universe collapses on itself. A general term for that is the big crunch. This would be the way universes die. What's going to happen? Galaxy is going to crash into galaxy. Star is going to crash into star. Any planets around those stars are going to be in big trouble. And it's going to crash back to, guess where? It's going to crash back to, perhaps, that primeval atom of Lemaitre. Or maybe back to that singularity. And then what do you think will happen? Just a gut feeling what's going to happen. It's going to do it all over again, because the concept of this one is that it's a cycle. It's a big cycle. Now, part of that theory says that we might not be the only universe. Out there could be other universes, some expanding like we are, some undergoing the big crunch and dying, others having just got back to the singularity or the primeval atom ready to start again, other primeval atoms or singularities ready to start. And so the idea is that we're not the only ones out there. And that sort of gives me sort of a fuzzy feeling to know that. So that's if we have the critical mass exceeded by. On the other hand, of course, if the total amount of known and dark mass equals a critical mass, they say that's the flat universe. It'll simply expand and come to an end, but it will never collapse.